Okay, we're going to take a look at properties of water. Water is essential to all forms of life on Earth. All living organisms require water more than any other substance. Most cells are surrounded by water, and cells themselves are about 70 to 95% water. The abundance of water, with its unique properties, is the main reason the Earth is habitable. Water is known as a polar molecule. When you look at a water molecule, the oxygen in the water molecule has a partial negative charge due to the electrons. Draw you a little water molecule. You know that water is known as H2O, meaning there's two atoms of hydrogen, and since there's no number on the oxygen, there's only one atom of oxygen. Well, when you look at a water molecule, you have your oxygen and then our two hydrogens. This is my hydrogen. This is oxygen. The oxygen is going to have a partial negative charge, and my hydrogens have a partial positive charge. So again, that's representing my water molecule. I have a hydrogen here and a hydrogen. Both have that partial positive charge, and the oxygen has a partial negative charge. Opposite charges attract, resulting in a hydrogen bond, but the oxygen is going to pull more than the hydrogen. This uneven pulling makes the water molecule polar. If we look at our little cartoon here, the oxygen is going to pull those hydrogens in closer. So here's my little oxygen again. This is oxygen. This is representing our hydrogen. If they were trying to hold hands and share evenly, there wouldn't be any tugging or pulling. But the oxygen's a little bit stronger, so he can pull those hydrogens closer to him. Since the oxygen can pull the hydrogens in closer to him, that's what's known as a polar molecule. Just for reference, nonpolar molecules, they're sharing evenly. If you had, let's say, two hydrogens without the oxygen, just a hydrogen molecule, you could have two hydrogens bonded together, kind of like if they were holding hands, but one's not pulling stronger than the other. One of them isn't pulling the other one closer. So this is what's known as nonpolar. But water represents a polar molecule, meaning one of the substances is going to pull the others closer. So the oxygen is pulling those hydrogens in closer. And then the hydrogen bond that forms, that's forming between different water molecules. And this is important to make sure that you keep this straight. This represents one water molecule. Your oxygen with your two hydrogens. Remember, water is H2O. This is representing a second water molecule. The hydrogen bond that forms between them is this dotted line. This is our hydrogen bond. Opposites attract. You have the positive on your hydrogen and a negative on your oxygen, and so the positive and the negative are going to want to attract together. They attract, forming that hydrogen bond. So again, and that's important for your EOC, the hydrogen bond does form between a hydrogen and oxygen, but in different water molecules. Continuing with that hydrogen bond, this is what's going to allow water to have some special properties. Our diagram, our first diagram here, this again is representing a water molecule and a second water molecule. where the purple ones are representing the hydrogens with their partial positive charge, and then the red is the oxygen with its partial negative charge. The positive charge on that hydrogen is going to attract to the negative charge on the oxygen, but a different water molecule. And in between these, this is where we get that hydrogen bond. The hydrogen bond allows for cohesion and adhesion. Cohesion, like co-workers. Water is attracted to other water molecules. Cohesion, two water molecules attract together, and that's like co-workers. Co-workers work together, so you've got two water molecules working together, a cohesion property. Adhesion, water is going to attract to other surfaces. Here we have adhesion represented. We have water, and it's on a leaf. That's a representation of adhesion. Think of adhesion like adhesive tape. Adhesive tape allows you to connect one substance to a different substance. So the water molecule is going to attach or be attracted to a leaf or a window or a different substance. The hydrogen bonds allow for capillary action. Capillary action is when you have a substance that's going to move against gravity, such as up through a straw or a tube. This picture is representing capillary action, blood moving through this skinny little tube. This skinny tube is actually called a capillary tube. Someone gets their finger pricked, and you can take the capillary tube, put it at the base where the finger was pricked, and that capillary action allows that blood to move up through the tube. You guys have probably done this with a straw. If you have a straw and you put in a drink, put your finger over the top of the straw and pull it out, you'll notice that there's some liquid in your straw. Again, that's a representation of capillary action. Cohesion and adhesion help with the transport of water against gravity in plants. The roots of a plant are going to absorb the water. The water molecules, again, they're going to clump together due to that cohesion property, and then they're able to move up the stem or the trunk in this case, but it could also be the stem of a flower, through tiny vessels known as xylem. Xylem allows for water and nutrients to move up through the stem or the trunk of a tree to the rest of the plant, in this case to the leaves. The adhesion allows the water to combine with the nutrients and then move into that xylem, and then the cohesion is the water molecules clumping together. Surface tension describes how hard it is to break the surface of a liquid. The cohesive property of water at the surface, along with the adhesive properties of the water with the air molecules, allow for a strong surface tension. Here we have the little stick bug. He's able to walk across the water due to that strong surface tension. You guys may have seen surface tension if you're filling a glass with water and you get that little bubble that forms over the top of the water. It's like you filled your glass all the way, but you went a little bit more and you have that little tiny bubble on the top of your glass. That's that surface tension that's forming. Water is unique in that it expands when it freezes. Usually a substance will shrink when it's frozen, but water's going to expand. This is going to increase the volume of the water, in this case the volume of the ice. As a result of increasing the volume, that's going to allow for the ice to become less dense. This is what is going to allow the ice to float on water. When a substance is more dense, it sinks. So the liquid water is more dense. it's going to stay at the bottom. Ice is less dense, it's going to float on top. This is what's going to allow for ponds and lakes in the wintertime, not here where we live, but up north, to act as an insulation. In this middle picture, this is representing the ice layer on top of a pond. When you have that ice layer forming, everything underneath it is going to be insulated, so it helps protect the wildlife that's underneath the ice layer during the winter time. This first picture, you're looking at the ice molecules. You'll notice that all of the water, they're all connected together. Every water molecule is connected. You can see all the dotted lines. Those dotted lines again are representing those hydrogen bonds. When you look at liquid water, you're looking at chains. If you kind of start with one of, here's representing just two water molecules attached together. Here we've got water molecules attaching. We've got another chain of water molecules here. Here's a chain. They're connected in chains, but they're not connected like you see in this spot. They're not connected there. There's no bond that's formed there, and that's the difference when you look at the liquid versus the ice or the solid. The solid's going to have connections with all of those water molecules, all interconnected together. Could you imagine if ice did not float? So then up north, if ice didn't float and it was more dense and sunk, then you'd have an ice layer that would sink to the bottom of a pond. Well, it's still winter time, so then you'd have another layer of ice forming, and eventually that pond would be solid because you'd keep getting ice layers and they would continue to sink. So it's pretty cool that water is going to be able to float on liquid water, again acting as that insulator. Water is known as a universal solvent. When you're talking about a universal solvent, we're referring to solutions. In a solution, you have a liquid with something dissolved in it. Lost my pen. When you look at a solution, you have a solvent, which is going to be the substance that does the dissolving. Then you have a solute. That's the substance that's going to disappear. It's what's getting dissolved. An example, if you were making instant tea or instant coffee, water would dissolve the instant tea or the instant coffee. So water's the solvent and tea is the solute. The tea or the coffee is what's getting disappear. It's going to dissolve. So that's the solute. Another example with Kool-Aid. Kool-Aid powder, that's going to be your solute. It's going to disappear, it gets dissolved. And again, water is going to be the solvent. It's going to do the dissolving. In looking at water, its ability to dissolve, you know that you can put sodium chloride, which is table salt, into water, and the salt water, you'll make salt water because that salt's going to dissolve in the water. This is because water is polar. It's going to attract other atoms to itself. So when I look at my water molecule, in my diagram, my water molecule, this is oxygen and the hydrogens. And then my sodium chloride, here's sodium and the chlorine. Together that makes sodium chloride, the table salt. The positive hydrogens are going to want to attract the negative chlorines. So these positive, remember the hydrogen's partially positive and the chlorines are partially negative here. So the hydrogens are pulling those chlorines away from those sodiums. And so when you look at your diagram now as it's dissolving, notice that my hydrogens are surrounding around a chlorine atom, the positive hydrogen and the negative chlorine. And then oxygen, remember, was negative. My oxygens carried that negative charge. Well, the sodium is carrying a positive charge. So again, my opposites attract. The negatives on the oxygen are going to attract to the positive sodium. So my oxygens are pulling the sodium out of the sodium chloride. Since this is representing dissolving and you're looking at a solution, the sodium chloride is going to be the solute. It's what's going to get dissolved or disappear. And then the water is the solvent. It's doing the work. It's doing the dissolving. And then the end result is going to be a solution of salt water. Specific heat helps to moderate the climate. When we talk about specific heat of water, water has a high specific heat. When summertime rolls around, people like to go to the beach because even though it's really, really hot outside, the ocean is going to stay fairly cool for a while until the very end of summer when it is finally going to warm up. But there for a long time throughout the summer, that water is still cool. It's because it takes a lot of energy to change the temperature of water. Then in the winter time, the water kind of stays warm for a while until the very end of the winter time. And so you'll see many people, even though the temperatures are a little cooler outside, they're still going in the water because it's still warmer, because it takes a lot of energy again to change that temperature of the water. This is what helps moderate our climate. If you listen to a news report, they'll say, you know, for example, in the summertime, they'll say Jacksonville's temperatures are 92 degrees Fahrenheit, but the beach is going to remain cooler at 89 degrees Fahrenheit. The beach is cooler in the summertime, again, because the water is cooler. It helps control the helps control the temperature of the air. And then in the winter time, we get the opposite. They'll say at the beach, temperatures are going to remain a little bit warmer. And again, that's because by the time winter rolls around, our water has warmed up some, and so that helps keep our air temperature warmer. Again, that's known as a high specific heat. It takes a lot of energy to change the temperature of water. And then water causes different pH values, resulting in acids and bases. In an acid and a base, just these are some examples listed for you. Tomato juice is acidic. A car battery has acid in it that's acidic. Lemon juice is acidic. Black coffee is acidic. Acids are going to have to release that hydrogen ion into the water. And then a base is going to remove the hydrogen from the water, creating a hydroxide ion. Another way to look at water, again, we know water is H2O, but that can also, we don't see this very often except in chemistry when you're studying acids and bases. A lot of times we'll write it as HOH. There's my two hydrogens and then my oxygen. And the reason they'll do this when you're studying acids and bases, because the acids are going to release hydrogen ions into the water. And so this hydrogen ion, this hydrogen basically is going to go put into the water, and then the hydroxide, which is this OH, is going to go into the bases. So when you have a lot, if you look at the picture, if you have a lot of OH values, see all the OHs in the beaker, that's indicating this is a base. Something like bleach, milk, oven cleaners. If you've ever had cleaner on your hands, you know that like soaps and bleach, they're very slippery feeling. Those are bases. And then if you have a lot of hydrogen ions, see all the H's There's way more H's here represented than there are OH. The H's meaning if you've got a lot of H's, you have an acidic solution. And then a neutral solution is when your hydrogens and your hydroxide ions are balanced the same. They're equal to one another. Any value that is less than 7 is considered acidic. In other words, an acid. Any value that is greater than 7 is considered a base or basic. And then your range falls between 0 and 14, with 7 being neutral. We have buffer solutions. Buffer solutions try to maintain that pH value, that normal range of 7. Buffer substances are things that are going to minimize the change in hydrogen and hydroxide ions. So these are going to prevent us from getting extra hydrogen or extra hydroxides in solutions. Most buffers consist of an acid-base pair that reversibly combines with hydrogen. Hydrophilic and hydrophobic substances. Hydrophilic substances is one that has an affinity for water. In other words, hydrophilic are things that like water, whereas hydrophobic is a substance that does not have an affinity for water. Hydrophobic, in other words, does not like water. Think of a hydrophobic as like a phobia, afraid of something. Hydrophobic means doesn't like water. And we'll take a look at the cell membrane. Cell membrane represents both hydrophilic and hydrophobic. One part of the cell membrane likes water, being hydrophilic, and one part is going to be hydrophobic, does not like water. Oil molecules are hydrophobic because they have a relatively nonpolar bond. Like usually dissolves other like substances. Water is polar, so water typically dissolves other polar substances. Oil is nonpolar, so the two of them do not mix together. Threats to the water quality on Earth. Acid precipitation, precipitation meaning rain, snow, fog. If it's acidic precipitation, it has a pH lower than 5.6. Acid precipitation is caused mainly by mixing of different pollutants with water in the air, and then they can fall at some distance from the source of the pollutants. So you could have something happening in one city, but because it's getting mixed with the precipitation, that rain would fall somewhere else, being acidic. Acidic precipitation can cause damage, life in lakes, streams. It affects the acid precipitation on the soil chemistry, which is going to affect the growth of the forest or any other crops that might be growing in that soil. Human activities such as burning of fossil fuels threatens the water quality. Carbon dioxide is released by fossil fuels through a combustion reaction. This is going to contribute to the greenhouse effect, which is the warming of the earth. It also has an acidification of the oceans, in other words, adding more acid to the oceans, which are going to affect the coral reefs, causing the coral reefs to become calcified. This is a diagram again just showing water molecules combining together. Again, it is important to note that your hydrogen bond that's forming is between the partial positive of one hydrogen and the partial negative on an oxygen of a separate water molecule. So this diagram has one hydrogen bond here, a second hydrogen bond. Here's a third hydrogen bond and a fourth hydrogen bond. This is representing different water molecules bonded together.